Hello, everyone, and thank you for attending today's webinar, Enabling On-Device Learning at Scale. This webinar is brought to you by Qualcomm and is a continuation of our webinar series on AI. My name is Pat Lawler. I'm a staff manager in technical marketing at Qualcomm Technologies, and I'll be the moderator today. Before we get started, I'd like to go over a few housekeeping items. At the bottom of your screen are multiple application widgets you can use, including a widget to download today's presentation. All the widgets are resizable and movable. The slides will advance automatically throughout the event. At this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A widget and then click the Submit button. We'll answer questions after the presentation. Also, if you're experiencing any technical problems, please type your issue into the Q&A widget, and we'll be glad to offer assistance. I would like to now introduce our presenter for today. Joseph Soriaga is the Senior Director of Technology at Qualcomm Technologies and part of Qualcomm AI Research. Joseph, please take it away.
All right, thank you very much, Pat. Thank you, everyone, for joining today. It's a pleasure to be able to talk to you about the research that we're doing at Qualcomm AI Research. What we'll be focusing on for the next 45 minutes or so is on-device learning and what motivates us, why we think it's crucial for scaling intelligence. And then we'll talk about some of the latest on-device learning research and some of the results that we've been doing. We will have some conclusions and also talk about some future directions and give you some hints of some ongoing work. We can't quite fill everything today, but we want to give you a flavor of all of this, and we're happy to take questions after this. I think it's important to start by saying, just acknowledging how much AI has pervaded in so many different applications. This is kind of a sampling that probably you encounter in a lot of cases where we can have interactions with our smartphone, our home, as we're doing video conferencing here today, of course, all the way to what's happening in infrastructure with cities, video monitoring, and so forth. And the more that we deploy, the more that there's a need for intelligence, for personalization, and you're building that into the experiences that were powered by AI. And as we do this, it's important to understand how best to scale this and how to maintain privacy as we deal with all the data at the edge devices. So at Qualcomm, on-device intelligence has been a paramount focus of our company and our research group. We can process data closest to the source, and this is a perfect complement to the cloud. Suffice it to say, it enables privacy by having things not dependent on a link to the cloud. We have some improvement in reliability as well. We can address lower latencies and increase the efficient use of the network bandwidth as key pillars of moving things to on-device. Now, going further, we're still going through this transformation of what we consider a connected intelligent edge. Processing data closer to the edge, of course, drives new system values because we have more functionality across both the cloud, the edge, and the device. And, or I should say the edge to edge cloud. And what I mean is, in the past, we've been kind of initially launched AI through the cloud and relied on a very good connection back to the cloud to be able to leverage algorithms from AI and ML. A lot of the training also has to be done in the cloud because of the compute-intensive nature of training. Now, today, we're at this partially distributed AI operating regime, where now we can introduce some capabilities in power-efficient on-device AI inference. But really, as we go into the future, it's important for us to think about the whole cycle of AI, where we can do training and inference and consider things like lifelong on-device learning. And just to give you a sampling of how things can be divided between the device and the cloud, and how you can enhance services. On the right is an idea of a lot of the common inference applications that are on device today, such as contextual awareness, computational photography, face detection, fingerprint detection. And really these are being able to leverage being close to the source of the data and give fast inference results and be able to interact with the user very quickly. And the benefit also is that these lower level perception techniques can reduce the requirement on bandwidth and latency when going back to the edge and the edge cloud or the central cloud. And then we can leverage that more for more semantic or higher level services like local network analytics or augmented reality or extended reality. And also can interact a lot with enterprise data and enhance the overall user experience. So with that all in mind, then let me talk more specifically about what I mean when I say on-device learning. So we know in machine learning that to build our algorithms, we go and we take a neural network, and then we build up a data set and we train our neural network on a specific task with this data set. We do this often offline in a cloud, and we hope that the data that we've collected reflects the target application where the algorithm will be deployed, such as a mobile device. Now, on-device learning is the notion that when we do deploy this data, this model, and it's operating in deployment, as it's exposed to the test data, we can also modify the model, adapt it to the statistics of the test data. In a sense, learning on the device as to what's happening. So why would we want to do this? Well, it has some benefits which you may be aware of, but we'll just state it here to keep everyone in sync. So first of all, we can continuously learn. So as data may change or shift relative to what we collected for our training set, we'll be able to improve the model's performance over time. We can also personalize to the data that may be specific to each particular user. One nice thing about these two aspects is that we can also preserve data privacy. We don't have to centralize the data and require users to comply with sending their data and storing it somewhere centrally. And also, what goes together with this privacy protection is that we can scale it better. So sometimes even just the notion of collecting a very large diverse data set can be expensive, and as AI is pervading to many more use cases, we may not want to continue constantly collecting very large data sets for every particular case. So we can have on-device learning to help us improve or maintain the accuracy whenever that original pre-trained model doesn't generalize well. So, of course, these benefits have trade-offs, and this is what we'll be giving examples and talking about our research in trying to overcome these challenges. As I mentioned, of the benefits, we have better examples than in the training data set. We also, interestingly, have the ability to run with smaller models now, because we can adapt them to the target data rather than having a very large model that can deal with very large sets of data in the training set. And then, of course, we can have a preservation of privacy during the model development itself. Now, the challenges are that local data can be limited. We'll talk about this a bit more. There's noisy labels. There's also class imbalance, so the examples that we want may not be distributed the way we want. There's an issue of overfitting or catastrophic forgettings, as it's referred to in literature. This idea is that we maybe have learned important aspects of the task from the pre-training data set, and we may forget them if we overfit to the local data too much. Training at the edge does have limitations on compute and storage. We'll address this in more detail. And also, we may not cover this today, but when adversaries are aware that devices are learning, there are ways that they may attack, knowing that it's training. And then when I talk more about what federated learning is, there are some aspects of communication that we need to keep efficient. So more detailed agenda for the rest of the talk. I will go into our research areas that address these key deployments. We'll start with Fushot learning, and then I'll talk about continuous learning, both in the sense of locally adapting the models. And then we'll have federated learning, where we can crowdsource among devices. And then we'll change gears a little bit and talk about the feasibility, trying to reduce the complexity of implementing training on device. So let me start with Fushot learning. So in Fushot learning, first of all, learning from limited data is crucial for this, because if we look at our kind of operating flow, we've trained offline, and then we deploy our model. And in many cases, we may be able to collect data, but if we want the data to be labeled with, say, user assistance, it may actually not be so plentiful, because that's somewhat of a laborious task for the user to label. Enrollment is one example where a user does label data we store. But when we have few shots, we can improve the target user's model using some concepts of Fushot learning. Here's an example, which is an interesting one and a motivating one. So think about using Fushot for personalization in a particular application known as keyword spotting. So in keyword spotting, the device may be listening all the time and applying ML continuously in search of whether or not a particular keyword like "Hey Snapdragon" was said. And then the challenge for keyword spotting is that the same word may sound differently, and there may be outliers in the accents when this word is said. Like data, even the word data, as you can imagine, among different English speakers could have very different accents. And so if the outlier accents are not captured in the training data set very well, then the performance may not be as good. So one way to address this with Fushot learning is to locally adapt the model to the user enrollments, and then we can personalize the model at enrollment time. It turns out that if we look at the detection rate for some of these outlier users where the accents are not quite captured well, they might even be 30% worse on average compared to the average. So how would we locally adapt the model? Well, at high level, this could be actually quite simple to describe. As you'd imagine, for training the global model, it's well known that you can build up a data set where many speakers say the keyword and also provide examples that are not the keyword, and we can train our model. And of course, we'd have a validation data set also for helping with other hyperparameter optimizations. And then when we deploy the model, when we have an enrollment where a user would, for instance, give some examples of saying the keyword or saying other keywords, then we can personalize the model with some local training to that data set. And then we have something that's targeting the local users better. Now, when we look at how this can perform, you can imagine that there are going to be many different models that are being used across all the different users. And we can look at the performance on average among the users with their personalized models. Now, what we see in general is that everyone has improved. The inliers don't suffer from training to their enrollment. And more importantly, the outliers, the ones that were not perhaps captured as well in the training data set, actually do quite well in their performance improvement. In this particular case, we've kind of seen this 30% improvement among these outliers. So the personalization and the Fushot learning can be a very powerful tool for addressing this. Now we can take this a step further in local adaptation, where instead of looking at just a few examples, we can try to collect data over a longer period. So in the right, what's changed is that now we may have multiple days of data and more plentiful samples. The drawback, though, or the challenge, is that the samples themselves may not be labeled as well as an enrollment. And they may also be a little bit noisier than the ideal user-collected data. So in continuous learning, the goal is to be able to improve this target user's model in a continuous operation with this unlabeled data. So in our research team, generally how we look at this problem, we have two major areas that we try to address. First, what do we do about this unlabeled collected data? The training doesn't have necessarily labels when we collect it on the device. So one solution we can apply is to assign pseudo labels to the training data. For instance, we could have a reference model or a teacher that's more capable to give us labels of the samples that we decide to collect. Another thing that is a challenge is we don't want to overfit to the small data. So even though the data is continuously collected, it may still be a small representation of the overall situation that can be encountered. And we don't want to, again, lose some of the important aspects of the algorithm and what the neural network has learned when it was pre-trained in the cloud. So one solution can be that we exploit a regularization loss so that we maintain some of the performance of that pre-trained model whenever we adapt it. And then we can also make sure to improve the more important metrics that are sensitive to the personalization. Now, these two previous examples are really in the notion of adapting a model locally, meaning user by user or device by device. If we look at a bigger picture of what can happen if we have devices that are capable of training, one nice thing is that if we further enable the devices to aggregate their model enhancements or adaptations, then we can have what's called federated learning. And this really can help bring on-device learning to another level, because we can have a global model that now improves from a more diverse data set, and benefits that each user saw from their local data set can be shared. So let me walk you through this. We start, of course, as we did before. We have a pre-trained model of state-of-the-art, and then it gets deployed to multiple devices that are capable of collecting data and also doing on-device training. So the benefit here is that we can scale. The processing can be spread over many devices. We can personalize because now we're reflecting the data that's on each device more accurately. And then we can also preserve privacy because the raw data is able to stay on the device as we do this training framework. Now, as the devices are updating their models locally, it's important that they go through a few steps. So first, they should do some kind of privacy preservation. So they can add a perturbation to the model parameters of their local update, something that's also referred to as differential privacy. And this ensures that the model update itself doesn't leak any of the particulars of the data that's stored. And then we can compress the parameters and encrypt them. And this is something that is typical of a communication system in general before we send that update back to the cloud. And then there's also a notion of secure aggregation, where the model updates are not necessarily able to be seen by the server, but the sum of the model updates are able to be seen and decrypted. And that helps to further protect the privacy and protect the model from leaking the information. So with this flow in mind, then we have that all the model updates can be aggregated at the cloud. Now, federated learning on 5G is a great way to scale intelligence, because as you can see, this overall communication flow can be optimized better on a network like 5G, where the focus has been on low latency, has been on good coverage, has been on power efficiency, and increasingly larger bandwidths. Now, one nice example of what federated learning can do is in the scope of user verification. And this is from a work we presented recently at ICML. So just to give some background, on user verification, we would like to use personal data to authenticate someone. You can think of a face image or a fingerprint, a voice, or even some other medical biometric. And of course, the authentication problem, if we use deep learning, we would need a lot of data to train a very powerful verification model. Like, for example, speaker verification, sometimes it can go upwards of 600,000 different speakers. So the challenge is, how can we learn this model while keeping all the data private? Even for the ones that want to participate in training, can we keep from compromising that biometric data? So if we think about a deep learning approach for authentication, this data would go through this function G, which is a neural network, to provide an output which is in a lower dimensional embedding space. And then we would want the inputs, the data inputs from a particular user, to be very close to the embedding vector of that user when we go through the neural network. And each of these would then help us to classify if it's user A or user B or user C. So as you can imagine, if we can enable this training of the neural network G with federated learning, this can be a powerful tool for expanding the applications of user verification. Now, in traditional user verification, we have to do, we essentially have to train our neural network with two losses in mind. So when we think about, again, those outputs from the neural network G of X, what happens is we would like that the neural network makes sure that the outputs from a particular user are close to the embedding that it's been given, the embedding vector that it's been given, but at the same time are far from the embedding vectors of different users. So in this picture, we would like to minimize the loss to the target user, so this gray line, but then maximize the loss to other users, these black lines. It turns out that in able to do this loss function properly, even if we're training locally at each user, we should have the embeddings shared among all the different users to properly do this loss function. Now, if we want to prevent having to share these loss functions, we can enable federated learning in a different way. We can actually use a structured embedding space, such as an error correcting code. And in this picture, what we do then is these embedding vectors W, because they come from an error correction code, they have a minimal spacing guarantee. And so that in these black lines helps us to ensure that these embeddings are going to be far apart. And so then when we're relying on the federated learning step of the users locally training the information, they only need to worry about making sure that their output embeddings are very close to their embedding vector. And they don't have to worry anymore about what the loss function might be to other users, because the error correction code has helped to ensure that the other users are spaced far apart. And so from this overall approach, we can just have federated learning where each user minimizes their own loss to their own embedding, and users don't have to share each other's embeddings with a server or with each other. And And so what we're able to achieve in what we call FedUV, which is what was in our paper earlier, is that we can have state-of-the-art verification performance against some other methods that are in literature. Let me walk you through this plot. So this FedUV for a particular embedding space of 512 turns out to be comparable to what we see is currently the best method, which uses a softmax and a one-hot vector space for all of the users. And here, the embeddings are actually shared among all the users when they calculate their loss function. Now, the goal in this plot is that we want a very high true positive rate for a given false positive rate, and the higher the better. As we can see, we're very close to a case where user embeddings are shared. Separately, we can look at another state-of-the-art method where the user embeddings are not shared with other users. This is Fed AWS, or average width spreading. And in this particular case, we see that we are getting a higher true positive rate and false positive rate. And it's because the benefit of having a better structure for spacing out the embeddings seems to improve the performance relative to this other approach, where the server has been given the embeddings and has a regularization to spread them out. So as you can see, we're able to demonstrate how we can do federated user verification model training. Now, another important aspect of our research group is we do want to look at what is a framework that we can do both research and application development on mobile. So in what I've shown you previously are experiments that we do in simulations, but we're also working to build a framework where model experts, machine learning experts, can work on PyTorch or TensorFlow, and then we'd enable them with the communication through a coordination server out to a bunch of mobile workers. The importance of this is that to be able to scale on-device learning and intelligence, we really need to be able to enable mobile devices. And so we've worked to provide a research training framework and support on mobile on Android. Another important thing is that we want a proper communication protocol in place so that we can use a Wi-Fi network or a 5G network and increase the coverage of which participants can be there, and also improve the energy efficiency of which they can communicate. And then finally, we do want to have a platform that readily supports PyTorch and TensorFlow, since those are two popular development frameworks for machine learning. So we've worked in this, and we continue to work in bringing this forward. We have a demonstration of this speaker verification application, which I showed in previous slides, and we've enabled this training framework on commercial devices like the Samsung Galaxy S21, which has been powered by Snapdragon's 888 mobile platform. So let me switch gears a bit, and then I'll talk about now how to reduce the complexity of on-device learning. So throughout the talk so far, I've kind of relied on being able to train and adapt the model with algorithm which is known as backpropagation. So being able to calculate the gradient, and then we update the model weights in the direction of the gradient. So as you may remember, when we do inference, we go through this forward pass where the input X goes layer by layer and activation by activation through until we get our final inference output. Now, when we do backpropagation, we do this calculation, and we also have to go backward and calculate the gradients layer by layer in a chain rule of differentiation. And this is the step that can be expensive computationally and has some requirements on it. As people may be aware, backpropagation has a large memory requirement because as we're going backward to calculate those differentials, we do need to keep track of the the activations that were done in the forward pass in most cases. And then also the training runtime can be slower depending on how the computation is implemented on the device and the computational capability on the device. Gradients themselves also require a higher precision for accuracy at times, and also the device itself may want to do quantized inference for better power efficiency, and so our training should be able to support producing a model that is quantized. So some of the solutions which we'll talk about today are we can reduce the complexity of backpropagation with quantization in the training. We can also look to have efficient models for backpropagation, something that can help reduce the activation memory requirement, for instance. And then we'll mention that you can also change the paradigm of how you adapt the model and use more inference type of methods to adapt the model. We won't really talk about that in detail, but it's important to acknowledge that this is another important way to overcome the challenges of efficiently adapting the neural network on device. So let's start with reducing the complexity of backpropagation when we look at quantization. So first of all, quantization in integer arithmetic has been a very successful way of improving the energy efficiency of inference on device and making AI more ubiquitous. Now, in the backpropagation, we can benefit from what we've done in the forward pass, but we have to extend it also to the backward pass, to the gradient computation. And the challenge, just as it was in inference, is we want to maintain the accuracy and ensure that we still reduce the compute and the memory. And so the solutions that we have, which we have in a recent paper that was at CDPR workshop earlier this year, is we can have quantization with in hindsight, what we call an in hindsight range estimation. And I'll explain that a little bit more. So existing techniques for quantized training can be too complex. And what I mean here is that the fixed point accelerators, when you think about how to implement the fixed point accelerators, the requirements to keep fixed point quantization can actually be not ideal for implementing them within those accelerators. And so as an important example, think about a particular layer, and we take from memory, say these weights at the top, W, and the gradient from the output from the previous layer, and we would run this through a MAC array and an accumulator. And if we just had a static quantization, then we could just take these outputs, the accumulator, and then before putting them in memory, we can quantize them directly into this gradient with respect to the input, in this particular case, g of x. Now, the drawback of having a static quantizer is, of course, that it can't keep up with the range of the backpropagation of the gradients themselves. A large dynamic range is needed for if we take a static approach. Another way to solve this is to have a dynamic quantization, so we can adapt the ranges on the fly depending on the data set that's being processed at a particular time. And if you see this table of performance, then the nice thing is that if we're doing this dynamically, then we can actually get very close to the performance of FP32 with either currently changing the min-max or having a running min-max that reflects the current or the previous. Now, one drawback of this, which may not be obvious, but as you think more about it, is that we do have to somehow get statistics on calculating the min-max. And this requires actually storing these intermediate calculations in memory and then calculating statistics before we can quantize them. So, in fact, it actually still requires a high memory transfer, even though we did get some benefits from being able to store the final gradient for that gradient component for that particular layer, and we can reduce the computations to just integer arithmetic. So what we can do in addition to this is think about having an online method where we have a delay in the system. And we can build into the accumulator a way of just calculating the statistics that we need to figure out the right range dynamically, but then just storing that range and applying it later in time. So that, in particular, in storing it in the next iteration. So that if you look back at this processing path, then we still have the nice benefit of the accumulator going through and quantizing regularly, where the quantizer has been preset from the previous iteration. And this allows us to reduce that memory transfer. And then if you read in our paper, there's some particular examples where we can reduce it significantly. And then still, as you see in this table below, have the benefits of being very close to floating point training just by doing this dynamic range estimation with a small delay. And the small delay, again, this is why we're calling it in hindsight, because it's looking back one step. Now, another approach that you can do, that is actually done in different applications already, in medical imaging, for instance, is to look at how to modify your model to be able to reduce the activations that need to be stored. So starting off with some background, when we look at backpropagation calculation, first on the inference side, we have our input x, which goes through these linear weights and its nonlinear activation function and gives us an output. And as we're doing this chain rule of differentiation, when we look at the loss functions, we do need to take a differential with respect to evaluate it at particular activation in the layer. This z, this activation, is what we need to have stored in memory as we're going through and calculating this layer by layer. And this is what can be a bottleneck in storing on the device, since this memory requirement may be too large for mobile devices or edge devices. So what we can do is introduce an invertible layer. So for the typical layer of a neural network on the left, we can have a different structure, which is very similar in the functionality and the expressiveness, but is invertible. So this x input can be divided in different ways into x1 and x2. And then we pass it through on one side, and then we run it through on x1, passes through, and then we can also run it through the weights and the activation on x2 to get y1. And as you can see, when we're working backward, we can reconstruct this z just by looking at the y2 output and running it through this calculation. Now the benefit here is that we can trade off a little bit more computation for reducing the need to store the activation in memory. And depending on the application, this can actually be the bottleneck and help us to be able to train on a device with limited memory. Now the challenge here is that we can introduce these, but we want to make sure that we still keep the number of parameters and other aspects of the model that's invertible just as competitive as the original model. So through a little bit more careful design, what we've been able to do in our research team is think about starting with MobileNet as an example, and then making sure that we still have the same number of parameters, the same number of max, and that we still get the same accuracy, but then overall still be able to reduce the activation memory. And then in this particular example, we really pushed it to see how far we can reduce the activation memory, which was 11-fold. So if the memory transfer is the bottleneck, or just not being able to store the memory, then we're able to reduce that. And you can also imagine this could even speed up training time, because if we reduce the amount of memory that we need to store, then we can actually have a larger batch size, and that may help us in the overall speed to convergence. So now that we've discussed different algorithmic approaches for dealing with on-device learning and how they can improve through personalization or global adaptation, and we've also talked about how we can make on-device training more efficient and feasible, you've had a sampling of different applications our research team is doing to be able to expand the use cases and the application. But this is just kind of a sampling, and it's important to get a sense of more of the things that we're looking at, and it's really a broad range of research in on-device learning. It's an exciting area in trying to get to the next level of scaling AI. So I talked a little bit about labeling and personalization. There is more that we can go along the lines of meta learning or active learning, and also dealing with noisy labels. In the notion of model updates that are local or in a federated sense, it's important it's important to see how to deal with tackling the statistical heterogeneity in the data. So we may not necessarily get the distribution that we want. Are there smart ways of combining the model updates from this broader distribution? We had some notions of privacy and security in some of the topics we discussed earlier, and as you looked at the operational flow that we had earlier. It is important to understand what the privacy guarantees can be and how to defend against adversarial attacks or detect anomalies whenever we're doing on-device training locally or in a federated manner. We, on the top right, in this on-device training efficiency, we talked about lightweight models. We talked about invertibility and quantization. There are still more angles to this and more variations of what we can do. We gave some examples just to give a good illustration of what's possible. In the space of federated learning, we covered how to further improve some of the privacy aspects in cases like user verification, where we wanted to be able to globally learn among users that don't see a wide diversity of data locally. And in addition to preserving that privacy, there are also ways of incorporating that with compression and further improving both the model update compression on the uplink, where the client is sending updates to the server, and also in the downlink, where the server is sending updates back to the client. And this can really help to further scale participation among federated learning. And then finally, we had a very simple connectivity diagram in federated learning, where we had one central server and we had many workers that were singly connected to that server. As you can imagine, there are a lot of other important topologies for federated learning, such as even peer-to-peer, a fully mobile or edge-based federated learning framework. We can think of multiple clouds or even a hierarchical level of privacy, so that we can trade off certain aspects of privacy where it might be okay to disclose some information up to a local edge point, but then we wouldn't want to disclose further information to a central cloud. So this gives you a feel for all the different areas of research that we're tackling, and we look forward to sharing this with you at future conferences and publications. And with that, let me conclude with just letting you know that on-device learning, again, we feel is really crucial to providing intelligent and personalized experiences without sacrificing privacy, and also helping us to scale up AI as more use cases are pervading and going across more devices in mobile and in edge and in IoT. And this gives you a feel for the research that we're doing in our group, and also the development toward on-device learning. And really our goal is to come up with solutions that can address the bottlenecks, but then also help us to solve the overall system and feasibility challenges, so that we can move our research toward commercialization. And with that, I'd like to conclude and leave this time open for questions. I thank you all for being able to spend time with me this morning and talk about on-device learning.
Thank you for the great presentation, Joseph. As a reminder, if you have questions related to the material, please submit them using the Q&A widget. We've already received quite a few, so let's get to the questions. First one, of the on-device research you presented today, which is showing the most near-term promise?
Sure. So let me address this question in a couple ways. So if I go back to like this larger categorization, where we have Fushot and continuous learning and federated learning, you can think of when we have local adaptation, these kinds of applications are you think more readily deployable because the overall system is a bit simpler. We just have to worry about one device and then dealing with its own data locally. And so we can tailor our algorithms and address the problems for that. And then, so in the near term, we feel like personalization is a solution that would come up sooner. Now, moving forward, once we have more devices that are actually capable of collecting data, keeping it private, and also adapting the models locally, and having this on-device training capability, then it's natural to expand this to federated learning, where we need to consider coordinating with the server and making sure that these updates are aggregated in the right way. And then, so with that in mind, if you were to go, to this broader range of research directions, then you can think about, in terms of enabling which directions are more applicable to, or more in line with local adaptation versus federated learning. You can start to see where we, in line with that, you can see thinking about on-device training efficiency, maybe where we hope to have this more readily, near-term in development, as well as thinking about dealing with, pseudo-labeling and personalization per device.
Great, thanks, Joseph. Next question. Do you expect traditional training with gradient descent will become mainstream on edge devices?
We do feel that, our overall vision of I go back to our kind of the beginning of the slide of the presentation. We do feel that the transformation, as I said earlier, it's important that we get to this fully distributed AI, where we do have on-device learning at the edge. And I think it's just a matter of, as we get more understanding of how we can improve these applications and adjust to the data that we have at the edge, then it will motivate more and more efficiency advances, so to speak, so that we can get some level of gradient calculation at the edge to be done efficiently so that we can modify our devices. It's hard to say, at this stage exactly when or where, but we do feel that it is a natural progression in how AI can continue to advance on the edge.
Thank you. Next question. Would these techniques also work for transfer learning of a given model that was trained for a generic purpose, such as feature extraction, but that needs to be tuned in the edge for a specific set of data which cannot leave the device for privacy reasons?
Yeah, that's a great question too. So if I come back to this idea of Fushot learning, a lot of literature also in Fushot learning is related to domain transfer and domain generalization. Dealing with domain shifts. And so certainly transfer learning is another example of where we could apply this, where you may train on a completely different data set, but it at least helps you to build good representations in the neural network that you want to deploy. And then we give it some carefully labeled examples, for instance, in Fushot, and then we allow it to say transfer to the same task, but maybe a different set of classes than what was trained in the cloud.
Great. I'm not sure if you can answer this one, but it may be hard to generalize, but but does federated learning use more or less energy than its centralized equivalent? Maybe you can just discuss some of the possibilities.
Yeah, sure. That's a great question. So, yeah, in federated learning, the first thing I should say is that there are different things that we brought up, like Fushot and continuous, that help to address generalization. So those are not kind of mutually exclusive from federated. You can do federated continuously if you wanted to, and keep updating the model as you collect data from the workers. That can help to address generalization as one approach. Now, with regard to the efficiency, in some cases you might be motivated to preserve the data only at the local device, in which case maybe the cost to efficiency of transferring the model updates back and forth may be worth it. On the flip side, what's interesting is sometimes the amount of data at the edge that you want to train on may be quite a lot, and the model update that you want, in fact, if you were to do transfer learning, for instance, you may not need to update the entire model. And it's important to, it allows you to scale down what you need to send to the network in order to learn what the model should adapt to. So there may be a benefit efficiency-wise where you want to do federated learning, especially given that once you know the task, you can even be more aggressive in compressing parameters for the model update. So these, again, can be very use case specific. And I think it's just important to acknowledge that there are use cases where you can benefit by sending a model update rather than the data, even from an efficiency standpoint.
Great. Changing subjects a little. Do you also tackle the catastrophic forgetting phenomenon, or do you perform a standard training?
Yeah, we talked about it kind of more briefly in this presentation, but what our research team, one example of trying to handle this is we would have some notion of the pre-trained data performance losses in different, with different example sets. And then so when we do adapt the model, we would want to make sure that the model does not deviate too much in certain metrics so that we don't forget important aspects of the task. And so this can be done through a different regularization, for instance. There are also some other approaches that are done in literature that can be applied. Our team is kind of exploring this, and unfortunately, because of time, we didn't quite cover all of them, or didn't have time to cover them. But you can kind of look through Qualcomm AI research, on our webpage, and see more of the things that come from our group in publication.
Okay. Next question. Can you provide any insight why Fushot learning with limited number of data samples is able to improve the outlier detection rate so dramatically for keyword spotting? Where else would Fushot learning work?
Yeah, that's a good question. I think in this, so this is a use case, things can vary by use case, but it's important to understand where potential improvements can be done for use cases, for certain use cases. Now, in this particular example, there are two important aspects that the Fushot is bringing to this. One is that we may not have had a diverse enough training set where some of these outlier accents were used in the training. So that's that's one drawback where if we can now get exposed to the test data, we can improve the accuracy. Now, another thing that is important is sometimes, especially when we're looking at mobile, we don't necessarily want to have a really large model, especially in this particular example where the model is on all the time. So if we were to have this really large data set with a diversity of accents, we would in turn probably need a large model to be able to capture all of the diversity properly and be able to infer whenever these appear. But it turns out in this particular example, we can take the other route where we have a smaller model and then we fine tune it to examples when they're outliers. And by looking at these two together, this is why we believe we saw a more dramatic gain in the system. So you could imagine that these could be kind of maybe even common limitations in other applications, because we may not be able to source a very large data set for many use cases. And also we may still want to be constrained to using a smaller model on the device for different tasks. So we feel that this is an interesting example, but also maybe something that may be more common that you can think about applying in your tasks as well.
Great, thanks, Joseph. How do you plan to address on-device learning for IoT devices with very limited hardware capabilities?
Yeah, very good question. So at the onset, the steps 1 and 2, which we talked about today, I think are important first steps for doing this. And depending on the IoT devices, what their requirements are. If it's a battery, then we can reducing the complexity of the backprop can be very important for saving that power. And then having a federation may be useful because then we can scale up to more devices and have less activity per device so that they can save power. And then step 2 is this efficient models, like building certain models to be lightweight, knowing that you have more constrained devices. It's another important angle that we feel can be pushed a bit further depending on what we need to do. And also understanding how much of the model we need to actually update for each task. Now, another thing we didn't talk as much about, but also can certainly find its way to IoT is there are other ways of approximately doing backpropagation or adapting the model using more of an inference flow. So not actually calculating a gradient, but somehow could be pruning the model, for instance, based on how it's operating on some of the test data at the edge. And then that could be leveraged for local adaptation, or it could be, again, crowdsourced through a federated learning framework.
Great, thanks, Joseph. Here's more of a clarifying question. For your technique of reducing activation memory, doesn't recomputing activations during backpropagation increase the total training time, which is prohibitive for edge devices? Yeah,
very good question. It's good to come back to that because the point, it is true, there is a trade-off where you are computing more so we would have to actually look a little deeper task by task, understand, is our bottleneck in storing all of the activation memory? Is our bottleneck in the bandwidth transfer, in getting the activations in the computation of the gradient? Or is the bottleneck in the computation itself? And so what this allows us to do is have a way of trading these off so that if indeed the activation memory is what's bottlenecking us, then we can introduce invertible layers and then have more compute. And here, this is an example in the extreme where we really pushed all the way to reduce the activation memory as much as possible. Now, it may turn out that if you were to operate in this regime, the training time may get slower because of the computation for a given batch size. But then the overall training to convergence, maybe you can win that back because when you did save the activation memory, maybe you could actually handle a larger batch size. So, and then that can help us to train to convergence in some cases faster. So it really is a more comprehensive problem that we have to tackle, but having more knobs and ways of attacking the problem is the important thing that our research team looks into so that we can trade these things off and really get the right performance for the task.
Thanks, Joseph. We're at the top of the hour. I'll throw in just one last question, maybe a quick answer. How necessary is the trade-off between energy consumption and the performance of on-device AI models when selecting a particular AI model?
I mean, from our standpoint at Qualcomm, we are very focused on energy efficiency and making AI ubiquitous. So it really is important to, to be able to, when we need to make that model efficient, make the calculations efficient, move to integer arithmetic and integer memory as much as we can. It is true, though, that it is possible that some devices may be plugged in, or they may be not as power constrained or compute constrained, and so you may be able to spend a little bit more in that direction, and then improve on other things, like maybe you can leverage that to train faster. So it is a constant trade-off, and like this previous slide on invertibility, we want to be able to have a good flexibility for different tasks that are to be designed for.
Great, thanks, Joseph. So that will be our last question. So on behalf of Qualcomm, oh, you're welcome. On behalf of Qualcomm and our presenter, thank you for joining us today. The webinar will be available on demand. The slides are available to download, and have a great rest of your day. Goodbye.
Bye-bye.